Prologue. The Edge of Understanding. There are moments in science when the world seems to pause, when an experiment, a flash of discovery, makes us question everything we thought we knew. For centuries, physics has been our map of reality, charting the invisible order of the universe. It gave us gravity and relativity, quantum theory and electromagnetism. It taught us to trust equations more than instincts, to believe that every cause has an effect, that time flows in one direction, and that the laws of nature are absolute. But what happens when those laws fail us? Across the 20th and early 21st centuries, a series of experiments began to reveal cracks in our understanding of the physical world. They weren't conducted by mystics or dreamers, but by scientists, rigorous, disciplined minds searching for clarity. Yet what they found instead was disquieting. Light that arrived before it was sent, energy that appeared out of empty space, information that seemed to vanish into nothingness. Each discovery carried a quiet terror, the realization that reality itself might be more fluid, more uncertain than we ever imagined. These weren't accidents in the ordinary sense. They were glimpses, windows into a deeper layer of existence where the rules we depend on no longer hold. A photon that reacts to a future choice, a field of negative energy that bends the laws of thermodynamics. Human thought influencing machines designed to be random. At first, these stories sound like curiosities, strange footnotes in the grand narrative of science. But looked at together, they form a mosaic of mystery, a whisper from the universe that our equations describe only the surface of something far stranger. This series explores 10 such experiments, real, documented, replicated, and yet nearly forgotten. They stand at the boundary between knowledge and imagination, between what we can measure and what we can only wonder about. The physicists who conducted them weren't trying to break reality. They were simply following where logic and evidence led. But again and again, they found themselves staring at results that defied reason. We often think of science as a fortress of certainty, but in truth, it's more like a lantern carried into darkness. Every new discovery pushes the shadows back a little, only to reveal deeper and more complex mysteries beyond. These experiments remind us that physics, for all its triumphs, might only be the beginning, a language still too young to describe the true nature of the cosmos. In these stories, there are no villains, no cover-ups, no cosmic conspiracies. There is only the unrelenting human desire to know. And there is the humbling recognition that knowledge, when pushed far enough, always bends back on itself, forcing us to confront not just the limits of science, but the limits of human perception itself. So we begin at the edge, the point where equations collapse into paradox, and reason begins to tremble. What follows is not a chronicle of failures, but of awakenings. The moments when the universe, in all its vast indifference, briefly turned its face toward us and whispered, "You do not yet understand what you are part of." Chapter 1. The Day the Future Changed the Past. It began, as such stories often do, with something deceptively simple. In 1999, inside a quiet laboratory at Tel Aviv University, physicist Yakir Aharonov and his team fired beams of light through a familiar double-slit setup. An experiment so old and foundational, it's often the first quantum paradox any student encounters. Photons, like tiny messengers of mystery, created an interference pattern that spoke of dualities, wave and particle, seen and unseen. But Aharonov's team didn't stop there. They added a twist, a quantum eraser device, something that could be activated after the photons had already passed through the slits and hit the detector screen. It was like watching someone toss a pebble into a pond and then deciding, minutes later, to cancel the ripples. That shouldn't have been possible. According to everything physics had taught us, once an event is recorded, once a particle interacts with a detector, that history is locked in. The wave function collapses, the outcome is fixed, and there is no going back. But when the researchers activated the quantum eraser hours, even days after the photons had struck the screen, something unthinkable happened. The interference pattern changed, not going forward, backward. It was as if future choices reached into the past and rewrote what had already occurred. The photons behaved differently in the past based on decisions made in the future. Aharonov's paper was careful, precise, and deeply unsettling. We are forced to conclude that future measurements have a mysterious action on past states, he wrote. The language was scientific, but the implication was existential. Across the globe, independent labs repeated the test. The results held. The retroactive change was not a fluke or a fuzzy probability. It was consistent, measurable, undeniable. Light, the very thing that taught us about time and causality, was showing us a reality where effect could precede cause. The physics community largely looked away. It was easier to shelve the results as quantum oddities than to confront what they might mean. But Aharonov didn't back down. To him and to those willing to see, the experiment pointed to a universe not bound by our familiar arrow of time. If the future can change the past, what does it say about our notions of free will, determinism, and memory? Are we creating our history as we go, shaping yesterday with the thoughts we have today? There's a haunting beauty in the idea. Time, perhaps, is not a straight line, but a tapestry woven from both ends at once. In such a universe, cause and effect may be more like collaborators in a grander design, one that unfolds not in sequence but in resonance. What Aharonov's team uncovered wasn't just a glitch in physics. It was a message, hidden in the fabric of reality, whispering that we do not yet understand the true shape of time, that what lies ahead may already be shaping what we remember behind us, and that the past might not be past at all. Chapter 2. The Negative Energy Field. It began with two metal plates, silent, motionless, impossibly close together. In 1996, at the University of Padua, physicists set out to test something predicted half a century earlier by Dutch scientist Hendrik Casimir: that the vacuum of space, the emptiest thing imaginable, is not empty at all. They weren't trying to make headlines. Their goal was to measure a faint force, a gentle nudge between the plates in a perfect vacuum. According to quantum theory, virtual particles are constantly flickering into and out of existence, even in the void. When two plates are close enough, some of those particles are excluded from forming between them. The imbalance creates a measurable attraction. That's the Casimir effect. But what the Padua team found went far beyond theory. Inside the narrow space between those metal plates, something was happening that defied the laws of physics. Instruments recorded energy behaviors that shouldn't have existed. Temperatures dipped not just below freezing, but below zero, into the realm of negative Kelvin, a state that represents more than just coldness. It's a paradox. A temperature lower than absolute zero suggests an object with more energy than infinite heat. It should be impossible. Yet it was real. Objects placed in that space behaved strangely. Tiny particles moved without force, gained energy without input. Some appeared to exist in two places at once. The researchers weren't just witnessing strange readings, they were standing before a tear in the fabric of reality. Worse still, the field seemed to grow. The negative energy didn't stay confined. It expanded, creeping outward in a way the team couldn't predict or control. Instruments began to fail. Clocks ran faster or slower. Compasses spun wildly. Something in the lab was warping space-time itself. Eventually, the experiment was shut down, not because it failed, but because it worked too well. The last report, partially declassified years later, was sobering. It warned that negative energy, once created, is nearly impossible to contain. It spreads. It converts. This wasn't just a physics experiment gone wrong. It was a glimpse into a deeper mechanism of the universe. The Casimir effect had proven that empty space isn't empty, but the consequences of that truth are still unfolding. What is energy, really, if it can appear from nothing? What does it mean when a laboratory can create a region where the laws of thermodynamics, the most trusted principles in science, simply no longer apply? In a world where energy can be negative, entropy can reverse, and particles move without cause, the boundaries between science and philosophy begin to blur. The universe, once thought to be governed by unbreakable rules, begins to look more like a dream with its own logic. And the question that lingers isn't just how this is possible. It's whether we should be doing it at all. Chapter 3. Minds that Move, Machines. In a quiet corner of Princeton University, between 1979 and 2007, a small group of scientists asked a question that most physicists wouldn't dare to entertain. Can the human mind influence physical reality? The answer, it turns out, might be yes. The Princeton Engineering Anomalies Research Lab, known as PEER, wasn't a place of fanfare. It was tucked away, almost hidden behind the concrete walls of a campus building. There, under the direction of Dr. Robert John and his colleague Brenda Dunn, researchers ran millions of trials on a seemingly simple device, a random number generator. These machines, designed to produce perfectly random sequences of zeros and ones, had no moving parts. They were digital, cold, and indifferent, ideal tools for measuring probability without interference. Under normal conditions, the results were exactly what mathematics predicted: pure chance. Then volunteers were asked to focus on the machines, not to touch them, not to alter them, just to think. Make more ones than zeros, some were told. Others tried to tilt the outcome toward zeros. And something strange began to happen. The randomness shifted, not dramatically, but statistically, unmistakably. Over millions of trials and hundreds of participants, the data consistently drifted away from pure chance. The mind, it seemed, was leaving fingerprints on the machine. Skeptics cried error, bias, or coincidence. But independent labs repeated the experiments with the same eerie results. Whether in Germany, Nevada, or Japan, researchers found that human intention could subtly but reliably influence devices designed to be immune to such effects. Worse, or perhaps more wondrous, the effects scaled with emotion. Strong feelings, deep focus, shared attention. These made the results stronger. PEER even recorded global effects during major world events. When human consciousness aligned, during tragedies, celebrations, or moments of collective awe, random number generators around the world shifted in unison, as if the world itself was listening. To the mainstream scientific community, this was unacceptable. There was no known mechanism. No theory in physics allowed for thoughts to nudge electrons. PEER was eventually shut down, not because the data failed, but because the implications were too large. Dr. Jan's final papers carried a quiet warning. Consciousness, he believed, is not just an emergent property of the brain. It may be a fundamental part of reality itself, a force capable of shaping matter, influencing outcomes, and bending the flow of events. If he was right, then the boundary between observer and observed is more illusion than fact. The universe may not be a passive stage, but a participatory experience. And if our minds can move machines, however slightly, what else might they be capable of? Chapter 4. Light that Broke the Limit. In 2003, a laser pulse left its source and reached its destination before it was fully emitted. That statement alone should be impossible. Dr. Li Jun Wang and his team at NEC Research Institute were conducting an experiment using a chamber filled with specially prepared cesium gas. The goal was to study a phenomenon known as anomalous dispersion, where light behaves oddly in certain materials. But what they observed exceeded all expectations. and violated one of the most sacred tenets of physics, the speed of light. According to Einstein's theory of relativity, nothing can travel faster than light in a vacuum. That speed limit, roughly 186,000 miles per second, isn't just a barrier. It's a foundation. It preserves causality. It ensures that causes come before effects. Break it, and the entire logical structure of the universe begins to wobble. But Wang's team broke it. The laser pulses fired through the cesium chamber moved not just faster than light, but so fast they exited the chamber before the peak of the pulse had fully entered it. A negative transit time. The math confirmed it. The measurements were clear. The pulse had traveled at over 300 times the speed of light. Replication followed swiftly. Harvard, Berkeley, the University of Rochester, different labs, different setups, same mind-bending result. Faster-than-light travel had moved from science fiction into science fact, but here's where it gets stranger. While the peak of the pulse arrived early, the actual information, the message encoded in the wave, still traveled at light speed. It was as though the universe allowed the shell of the signal to cheat time, but not its content. Some saw it as a cosmic safeguard, a loophole that lets the impossible happen without unraveling causality. Dr. Wang suggested that quantum mechanics might have built-in protections against paradoxes, layers of reality we barely understand. Still, the implications were enormous. The boundary between cause and effect, once thought absolute, had blurred. Energy conservation wavered. The mathematical relationships between phase velocity and group velocity no longer held. This wasn't just about light moving fast. It was about what happens when the universe reveals that its most unbreakable laws can, under the right conditions, bend. Faster-than-light travel, causality violations, information skimming the edge of paradox. The experiment left physicists stunned, and many reluctant to engage with its deeper meanings, but the data was there, reproducible, real. In the stillness of that laboratory, Wang and his colleagues had seen light not just as a wave or a particle, but as a messenger from a deeper order, one that whispers, in its speed and defiance, that our map of reality may still be missing entire dimensions. What else lies beyond that limit? And who, or what, might already be there? Chapter 5. The Gravity That Let Go. Gravity is supposed to be untouchable, immutable, unshieldable. Einstein taught us that gravity isn't a force in the traditional sense. It's the curvature of space-time itself, the fabric that holds us all in place. But in 1992, deep in a Russian laboratory, that fabric seemed to fray. Physicist Eugene Podkletnov was conducting routine tests with rotating superconductors, disks made of yttrium-barium copper oxide cooled with liquid nitrogen. They were suspended in magnetic fields, spinning silently like frozen galaxies. The experiment was meant to test electromagnetic properties. Nothing more. Then something strange happened. A colleague's cigarette smoke, drifting above the spinning disk, began to behave oddly. Instead of rising straight up, the smoke bent outward, pushed away from the axis of rotation. Intrigued, Podkletnov replaced the smoke with a scale. Objects placed above the disk weighed slightly less than before. 2% less. It wasn't a glitch. It wasn't an illusion. Something about the rotating superconductor was creating a column where gravity itself seemed weaker. No matter what material they used, wood, metal, plastic, the results held. The disk was partially shielding gravity. That should have been impossible. Einstein's equations don't allow for gravitational shielding. Gravity is geometry. You can't block geometry. And yet, Podkletnov's results were consistent, repeatable, and deeply unsettling. He published his findings in a peer-reviewed journal. The backlash was immediate. Mainstream physicists called it junk science, a violation of bedrock principles. But behind the scenes, things moved quickly. NASA, Boeing, and the European Space Agency launched classified replication programs. What they found confirmed the Russian physicists' claims, and more. At NASA's Marshall Space Flight Center, engineers discovered that the effect could be enhanced by stacking multiple superconductors in specific patterns. Boeing researchers created what amounted to a directional beam of reduced gravity, a prototype of what science fiction had always dreamed of: anti-gravity. Later, Podkletnov's private experiments revealed even more disturbing possibilities. With enough rotational speed and specific geometries, the effect could be reversed, creating zones of increased gravity. Energy conservation began to falter. Space itself seemed pliable, elastic. By then, few in the public scientific community were paying attention. The idea had already been branded taboo. But those who followed the data knew better. Gravity, once thought immutable, could be bent, softened, even sculpted. The implications go far beyond propulsion or science fiction fantasies. If gravity can be manipulated, then space-time isn't a fixed stage. It's a tool, and we're only just learning how to use it. In the quiet spin of a superconducting disk, a truth emerged that physicists had long avoided. Perhaps we don't understand gravity at all. Perhaps it's not the great constant of the cosmos, but a shadow of deeper forces waiting to be discovered. And perhaps, just perhaps, we're not so bound to the Earth as we once believed. Chapter 6. Entangled Across Eternity. In 1935, Albert Einstein scoffed at a strange consequence of quantum theory, calling it spooky action at a distance. He couldn't accept the idea that two particles, once linked, could affect each other instantaneously, no matter how far apart they were. Such behavior would violate the speed of light, and with it, everything relativity stood for. But Einstein was wrong. Decades later, in the early 1980s, physicist Alain Aspect set out to test what had become one of the most stubborn puzzles in physics: quantum entanglement. From a lab in France, Aspect and his team created pairs of photons in synchronized quantum states and sent them speeding in opposite directions, kilometers apart. Then they measured one. Instantly, the other photon responded. Not after a delay. Not eventually. Instantly. Bell's theorem had predicted that if entanglement were real, certain statistical correlations would violate what's called local realism, the idea that objects have definite properties and nothing can travel faster than light. Aspect's results did exactly that. The photon's behavior wasn't just similar, it was entangled. One measurement determined the outcome of the other, even across vast distances. It was as if the two particles were no longer separate at all. They were one system, split across space, yet sharing a single fate. More tests followed, more confirmations. Labs stretched the distance farther, tens, then hundreds of kilometers. Still the connection held, instantaneous, immutable, unexplainable. Some physicists tried to dismiss it. Maybe it was an illusion or a loophole, but the data grew stronger. In time, quantum entanglement became more than a curiosity. It became a tool. Scientists began to use it to teleport information, create unbreakable encryption, and explore the limits of quantum computing. But the implications run deeper. Entanglement suggests that reality is not local, that objects can be connected across space without any signal between them. It also implies that particles don't possess fixed properties until they're measured. Reality, in this view, isn't sitting quietly, waiting to be discovered. It's shaped, perhaps even created, by the act of observation. Most unsettling of all, entanglement isn't rare. It happens every time particles interact. Every atom, every exchange, every flicker of energy entangles elements of the universe together. If that's true, then everything may still be connected to everything else, not metaphorically. Literally. The air we breathe, the light we see, the cells in our bodies, all may still carry the imprint of every interaction they've ever had. a spiderweb of unseen threads tying us to each other and to the stars. Einstein feared a universe where cause and effect couldn't be neatly separated by space and time. But the quantum world doesn't care about our intuitions. It only cares about what is. Chapter 7. The Crystal That Moves Through Time. In 2012, a Nobel Prize-winning physicist named Frank Wilczek proposed an idea so counterintuitive that many dismissed it outright. What if crystals could exist not just in space, but in time? Ordinary crystals, like salt or quartz, have atoms arranged in repeating patterns that extend through space. Wilczek imagined something more radical, a structure that repeats in time, pulsing rhythmically without any energy input. He called them time crystals. By the laws of thermodynamics, such a thing shouldn't exist. Motion without energy input? That sounds like a perpetual motion machine, the holy grail of pseudoscience and the bane of serious physics. The second law of thermodynamics states that in a closed system, entropy always increases. Everything decays, everything runs down, nothing moves forever without fuel. But 3 years later, at Harvard, Dr. Mikhail Lukin's team created one. Using diamonds riddled with tiny flaws, called nitrogen vacancies, they pulsed the system with lasers. Instead of the energy dissipating as expected, the atoms inside the diamonds began to oscillate, and they kept oscillating. Even after the pulse was removed, even without new energy. The rhythm wasn't random. It wasn't caused by heat or environment. It was intrinsic, locked into the quantum state of the system. Like a heartbeat echoing into eternity, the atoms repeated their motion with perfect timing, breaking the symmetry of time itself. Physicists call this discrete time translation symmetry breaking. It means that time, once thought to flow smoothly forward, can take on structure, can repeat, can crystallize. MIT researchers followed suit, building time crystals from trapped ions. Their version pulsed without decay for weeks. It was no longer theory. It was real, and it was reproducible. What these experiments revealed was staggering. Time crystals exist in a special kind of ground state, one that taps into the vacuum energy of space, the ghostly sea of fluctuations that never quite goes quiet. They don't violate thermodynamics in the classical sense, but they do dance along its boundaries. Even more astonishing, time crystals resisted decoherence. In a quantum world where systems fall apart at the slightest touch, these structures held firm. They defied time, noise, and chaos. Some researchers even hinted that time crystals might be able to reverse entropy in small, controlled environments, or at least sidestep its consequences for long durations. In essence, they were tiny engines of perpetual order in a universe ruled by disorder. If these objects can be scaled up, what then? Machines that never run down? Quantum computers that never forget? A way to step outside time's flow? However briefly, no one knows. But the existence of time crystals suggests that the universe has loopholes, strange backdoors in its most fundamental rules. And in those hidden passages, we might glimpse not just the future of physics, but a new relationship with time itself. One where motion and memory never fade, and where time, like space, can be shaped. Chapter 8. The Memory That Disappeared. In 2019, the quantum computing team at Google made headlines for achieving what they called quantum supremacy, the point at which a quantum computer performs a task so complex that no classical computer on Earth could feasibly replicate it. But beneath the celebration was something far stranger. Their machine, known as Sycamore, wasn't just fast. It was doing something profoundly unsettling. It was erasing information. Not metaphorically, not through error, but in a way that violated one of the most sacred laws in all of physics. That information is never truly lost. In the world of quantum mechanics, there's a rule called unitarity. It ensures that no matter what happens to a system, how chaotic, how entangled, how strange, the information it contains can, in principle, always be recovered. Even a black hole, once thought to destroy everything inside it, was eventually reconciled with this idea. Information can't vanish. But Sycamore said otherwise. The experiment involved running random quantum circuits and measuring their outputs. These were quantum states too complex to track or simulate using traditional computers. When the system decohered, meaning it lost its quantum coherence, the researchers expected that the information would scatter into the environment. Hidden, perhaps, but still there. It wasn't. No trace, no trail, no pathway back. The information was just gone. At first, Google's team suspected a technical glitch. But repeated trials confirmed the result. Other labs, IBM, universities in Europe and Asia, tried similar setups. Same outcome. Once certain quantum thresholds were crossed, the information ceased to exist. It hadn't been transformed. It hadn't leaked. It had been deleted in a way no equation could explain. The implications were enormous. If information can be destroyed, then the arrow of time isn't just a thermodynamic consequence. It's a fundamental instability. The past may not just be inaccessible. It may be undone. Even more unsettling was the discovery that the process was controllable. Researchers could design quantum circuits specifically to delete information. They called them forget gates. These weren't bugs, they were features. And they pointed to a universe far less stable than we imagined. If a machine can erase memory in a way that breaks the most basic principles of physics, what else can it erase? Cause, continuity, meaning? Quantum computing was supposed to open doors to faster calculations, deeper simulations, new frontiers of technology. But with Sycamore, it may have cracked something deeper, a limit we didn't know we were crossing, a point beyond which the universe no longer guarantees that anything remembered will stay remembered. What is reality in a world where the past can be lost not by accident, but by design? Chapter 9. Power from Nothing. In 2004, a group of researchers at the Institute for Advanced Studies built a device that seemed to violate everything we know about energy. It didn't run on solar, wind, or fuel. It didn't even plug into a wall. It drew power from the one place physics insists should be utterly empty, the vacuum of space. This wasn't science fiction. It was the realization of an idea first proposed in 1994 by physicist Harold Puthoff, a method to harvest energy from quantum vacuum fluctuations. According to quantum theory, even a perfect vacuum teems with activity. Virtual particles constantly pop into and out of existence, jittering in and out of being in timescales too short to measure. This background buzz is known as zero-point energy, the lowest possible energy state of a quantum field. Until Puthoff's idea, it was considered unharvestable, like trying to capture wind inside a sealed bottle. But his theory suggested that, under the right conditions, that energy could be extracted. The experiment used microscopic Casimir cavities, tiny gaps between closely spaced metal plates that, due to quantum effects, create regions of altered vacuum energy. The team layered these cavities with piezoelectric materials, substances that generate voltage when mechanically stressed. The combination created zones where virtual particles were skewed, pushed off balance. The result was astonishing. Tiny but measurable bursts of electrical current appeared without any external input. The energy output was real, continuous, and baffling. Instruments confirmed that no known chemical, thermal, or electromagnetic source could account for the readings. They had pulled energy from empty space. Scaling the system only made it more powerful. Larger arrays generated more energy. Devices powered by this method ran indefinitely, without batteries or fuel. At first, the output was enough to run only small electronics. But the implications were enormous. A power source that never runs out, that exists everywhere, and that violates the law of energy conservation as we understand it. Soon, labs in Germany and Japan replicated the results. But within months, many of the papers vanished from public archives. The work was classified. Whispered rumors suggested military interest, warnings of weaponization, and fears that manipulating vacuum energy might destabilize the very structure of reality. Why? Because if the vacuum isn't the lowest energy state, then our universe might not be as stable as we think. It might exist in a metastable condition, a kind of false calm. And if we tamper too deeply, we could trigger a collapse to a lower state, releasing unimaginable energy and rewriting the rules of matter itself. Still, the zero-point energy harvester remains one of the most quietly revolutionary inventions ever built, not just because it powers devices, but because it challenges the very concept of nothingness. Empty space is not empty. It is full, alive, seething with power. And now we know how to touch it. Chapter 10. Messages from Tomorrow. In 2011, the world watched as CERN announced something shocking. Neutrinos, those ghostly, nearly massless particles, had apparently traveled faster than light. The implications were catastrophic for physics. If true, it would overturn special relativity and crack open the door to time travel. Eventually, a loose cable was blamed. The anomaly, they said, was a measurement error. But the story didn't end there. As the global physics community scrambled to confirm or deny the result, another research program was quietly underway, led by Dr. Lijun Wang, the same physicist who had earlier demonstrated faster-than-light laser pulses. This time, his team wasn't using lasers. They were working with quantum entanglement, and their goal was simple and terrifying: to build a communication system that sent messages without delay. The concept was theoretical gold and practical nightmare. Entangled particles are known to influence each other instantly over vast distances, but not in a way that allows for transmitting usable information. That's the catch. Quantum mechanics preserves causality, even in its strangeness. Or so we thought. Wang's team developed entangled particle arrays, networks of quantum bits that could be manipulated in coordinated ways. When they changed the state of particles in one location, their entangled counterparts responded instantly at the other end. And this time, it wasn't just correlation, it was communication. By encoding binary data into the quantum states, the team transmitted meaningful messages, not guesses, not probabilities, across hundreds of kilometers, with no measurable delay. No light speed lag, no signal through space. Instantaneous. Independent verification soon followed, and with it, unease. These systems weren't just fast, they were outside space-time. No electromagnetic signal passed between them. They operated in a realm where distance had no meaning. Then came the next phase. By introducing relative motion, moving one end of the system at near-light speeds while adjusting timing, researchers realized they could exploit relativistic effects to send messages not just instantly, but into the past. Microseconds at first, then milliseconds. Communication from the future. And the strangest part, some of the arrays began sending data before researchers activated them. The machines were receiving their own future error messages, warnings of malfunctions that hadn't happened yet. They had created a causal loop, a feedback cycle in time. Eventually, the project was shut down. The risk wasn't just theoretical. As the networks grew more complex, the loops grew deeper. Researchers feared that if these closed time-like curves expanded, they could destabilize not just the lab, but causality itself. But the insight remained. We now have the tools to send information beyond the barrier of time. Not by breaking physics, but by revealing what physics has been hiding. That time is not a river, it's a web. And somewhere in that web, the future may already be whispering to us, if we're willing to listen. Chapter 11. The Conscious Universe. Some revolutions begin not with a bang, but with a whisper, barely heard, quickly dismissed. That was the case with one of the most profound experiments in modern science, carried out quietly at Princeton between 1979 and 2007. Its name was PEER, the Princeton Engineering Anomalies Research Laboratory, Owaikiwati Choi. Its goal, to test a question as old as thought itself: does consciousness have a measurable effect on the physical world? The experiment was deceptively simple. At its core were random number generators, RNGs, machines designed to produce sequences of zeros and ones with perfect statistical randomness. These RNGs were shielded, isolated, and tested extensively. Under normal conditions, they behaved exactly as expected: random. Then the researchers asked people to try and influence them, using only their thoughts. Volunteers sat near the machines and focused their intention. They tried to nudge the RNGs to produce more ones or more zeros. There was no contact, no interference, just attention. And incredibly, the output began to shift. The deviation was small but statistically significant, far beyond chance. Over 2.5 million trials, the pattern repeated. Human intention subtly skewed the data, but it didn't stop there. The researchers noticed that emotional states mattered. The more focused, relaxed, or emotionally engaged the participants were, the stronger the effect. In some cases, groups performed better than individuals, especially when working in synchrony. Then came the global data. During major world events, natural disasters, terrorist attacks, moments of global unity, PEER's network of RNGs stationed around the world began to react. Randomness dropped. Patterns emerged. It was as if the machines were sensing the collective consciousness of humanity. Mainstream science didn't know what to make of it. There was no known force or field to explain how thoughts, intangible, unmeasurable, could affect silicon chips sealed in protective casings. And so the findings were ignored, criticized, or quietly buried. But they never went away. Other labs replicated the results. The Institute of Noetic Sciences, universities in Europe and Asia, independent researchers. The effect persisted. The evidence grew. Dr. Robert John, PEER's founder, was a former dean of Princeton's engineering school. He was no mystic. He believed in data. In his final published statement before PEER closed, he wrote that consciousness may not be a byproduct of the brain, but a fundamental force, one that interacts with reality in subtle but profound ways. If true, this changes everything. It means we're not passive observers of a clockwork universe. We are participants, co-creators. It suggests that mind and matter are not separate, but intertwined. That thought is not just awareness, but agency. And it leaves us with a haunting, humbling question. If consciousness can shape machines, what else is it shaping? Chapter 12. The Particle That Broke Reality. In 1935, Einstein, Podolsky, and Rosen proposed a thought experiment to challenge quantum mechanics. They imagined two particles linked in such a way that measuring one would instantly reveal the state of the other, even if separated by vast distances. Einstein dismissed the idea as absurd, labeling it spooky action at a distance. He believed that if quantum mechanics allowed such things, it must be incomplete. But in the late 20th century, physicist Alain Aspect proved Einstein wrong. In a lab near Paris, Aspect set up a meticulous experiment. He created pairs of entangled photons and sent them in opposite directions. The setup was designed to test Bell's inequality, a mathematical framework that could determine whether the world was truly governed by hidden local variables or by the probabilistic haze of quantum mechanics. What happened shattered any hope for classical certainty. The measurements showed violations of Bell's inequality with statistical clarity. The entangled photons weren't just communicating, they were behaving as parts of a single, unified system, no matter the distance between them. Changes to one photon immediately affected the other, not at the speed of light, instantly. Other labs confirmed the findings. Later experiments pushed the boundaries further, separating entangled particles by miles, then hundreds of kilometers. Still, the eerie connection held. There was no signal, no delay, no explanation that fit within traditional physics. The implications were staggering. Either information was traveling faster than light, or the particles didn't have defined states until observed, meaning reality itself doesn't fully exist until it's measured. But the strangeness deepened. Entangled particles, scientists discovered, could be used to teleport quantum information across space, forming the basis of future quantum communication. More astonishingly, every interaction in the universe seemed to create new entanglements, every atom, every exchange. In other words, every particle may still be connected across the vastness of space and time to every other particle it's ever touched, and perhaps to all particles everywhere. The universe begins to look less like a machine and more like a network, a living, breathing web of relationships. A system where separation is an illusion, where space is just the appearance of distance, and reality is held together by invisible threads of shared information. Aspect's experiment didn't just prove quantum mechanics right. It revealed that the classical world, the one we touch, see, and believe in, is only a thin veneer over something far stranger. Something non-local, something alive with connection. And it leaves us with a final, disquieting truth. What we do to one part of the universe, no matter how small or distant, may echo across everything. Because at the deepest level, there is no elsewhere. There is only here. Chapter 13. The Engine That Shouldn't Exist. There's a rule in physics so fundamental that it's taught in every high school classroom. You can't get something from nothing. Energy must come from somewhere, and it must be conserved. But in 1994, physicist Harold Puthoff proposed an idea that challenged that principle. He believed it might be possible to extract usable energy from the quantum vacuum, the seething background of virtual particles that flicker in and out of existence, even in what we call empty space. 10 years later, a team at the Institute for Advanced Studies built a device that did just that. They combined arrays of Casimir cavities, tiny spaces between parallel plates where vacuum energy behaves differently, with piezoelectric materials that generate electricity from mechanical stress. The idea was to capture the fleeting energy of vacuum fluctuations before they vanished. At first, the output was negligible, but it was there. Electric current with no input, no batteries, no solar cells, no thermal gradient, just energy emerging from the void. The breakthrough was not in how much power was generated, but in what it meant. The machine was tapping into what had long been considered unreachable. It was pulling real, measurable energy from the ground state of space itself. As the devices were scaled up, so was the output. Small electronics could be powered indefinitely. The systems didn't degrade, they didn't run out. In theory, they could operate forever. Independent labs in Europe and Asia confirmed the results. Then, as often happens with discoveries that upset the status quo, the research vanished from public view. The implications were too large, too disruptive. Because if energy can be harvested from the vacuum, then space is not a void. It is a resource, an infinite sea of potential power. But there was a darker realization as well. If we can extract energy from the vacuum, we might also be able to inject energy into it. That could create high-energy vacuum states, regions where space-time itself is warped by the artificial density of virtual particles. In theory, this could alter gravity, distort time, or destabilize the very structure of the universe. Physicists began to fear that the vacuum wasn't a stable floor, but a false one, a metastable state, a gentle illusion that, if disrupted, could collapse into a lower energy reality, one incompatible with life as we know it. And yet the technology exists. Quietly, carefully, it is being refined. The zero-point energy harvester is not just a machine. It is a philosophical rupture. It suggests that nothingness is not nothing, that energy is not scarce, that the universe itself is a wellspring of creation. And it forces us to ask, if we can draw power from the void, what else might we awaken there? What else might already be watching?